Hi folks. So we're coming back to RMA, which is rotational motion in astrophysics. We've completed earlier the rotational motion part of this, and so now this starts the astrophysics part of the course. We're going to go through this until we get to the end, and then we'll then go back to do the remainder of Unit 3, which will be capacitors and inductors. As I mentioned in the post, there's some experimentation that we can do with capacitors and inductors, which we'll leave until we go back into school to get that done. So, astrophysics, and we're going to start the astrophysics bit by looking at gravitation. Now, you'll have done quite a bit of this already, from way back to the very early beginnings of your time in secondary school even, when we were talking about the difference between weight and mass. So obviously the weight is the force that the gravitational field will exert on a mass that is in that gravitational field, although at the time we wouldn't have put it quite like that, but we would have defined it in some much simpler way, but that's what weight is. Then, as we go into National 5, we start defining gravitational field strength. Weight is mass times gravitational field strength, W equals mg. We would have also drawn the similarities and said that that's pretty much exactly the same as what Newton's second law would be, F equals ma. And then taking it to that next step further, we had in higher, where we were looking at Newton's inverse square law of gravitation, and I'll go through all this in the page in a minute, but this is the sort of evolution that we've been doing, and we've been looking at gravity for quite some time, but in an ever increasing depth of understanding. And so this is, well, as far as you go and as we'll go with this part. But let's go and have a look at the learning intentions and see what they've got to say. So, well, the first one in this section 4, gravitation, I can convert between astronomical units and meters and between light years and meters. Okay, I'm not going to spend too much time doing this. In fact, I'm going to do it now. An astronomical unit is the distance between the Earth and the Sun. If you know that, then you can then just use a ratio, you just use a conversion factor to figure out the distances for any objects within our solar system. We wouldn't generally use astronomical units for any object that's outside of our solar system. Light years and meters. Now, a light year is defined as the distance that that light will be able to travel within 1 year. And so if light travels at 3 times 10 to the power of 8 meters per second, and if you know how many seconds there are in a year, then you'll know the distance that light can travel in 1 year. And that's what 1 light year is. It's an actual distance. It's not a time. Okay, but I'm sure you know that already. I mean, again, this is stuff that's in higher. Now moving on more to the advanced higher stuff, I can define gravitational field strength as the force acting per unit mass. And what I'm going to be doing is that this is a chicken and egg thing a bit, that as in Unit 3, when I was talking about electric fields and magnetic fields, I was referring to gravitational fields as an example of an electric field, because they're very similar. And so now I'll refer back to your work on electric fields when I'm talking about gravitational fields, because a lot of the physics is the same. We just have M's in place of Q's, which I'm sure you'll know what I'm talking about. So gravitational field strength is the force per unit mass. You can sketch gravitational fields, 4.3, you can sketch gravitational fields and field line patterns around objects. Okay, that's fine. I can use appropriate relationships to carry out calculations involving gravitational forces, masses, and their separations. Now, this is the higher formula, so Newton's inverse square law of gravitation, which again is shown in 4.5 there. Period of a satellite will come to a bit later on, and the rest of them again a bit later on. So we're going to start gravitation by, well, I guess going back to the very beginning, and this would be, I guess you're standing on the surface of Earth, and you will have a mass. So let's just say that you are 50 kilograms. Then what would happen is, because your mass is interacting with the gravitational field of Earth, the Earth would be applying a force to you, and that force could be calculated with the formula of W equals mg. Obviously 50 times 9.8 would give us 490 newtons. And so what this tells us is that standing on the surface of the Earth, where what we would call a gravitational field strength of 9.8 newtons per kilogram, or we could also use 9.8 meters per second squared, standing on the surface of the Earth would apply a force of 490 newtons, and that force would be acting downwards to there. Now, Newton's third law states that for every action there must be an equal and opposite reaction, and so it works both ways. If the Earth pulls you down with a force of 490 newtons, you must pull the Earth up with a force of 490 newtons as well. It's just the Earth is so big that you don't actually notice the Earth rising up to your feet. Whereas because you're quite small and puny compared to the Earth, you do notice it. Moving on from this, then we obviously, this was our sort of national 5 work. But then when we started looking at it in higher, and this formula works, but it only works so far, and the problem is because gravitational fields are not uniform fields. Now, in the electromagnetism unit we were looking at, between two parallel plates we would have a uniform field, and in any distance between the two plates the forces acting on the object would be the same. But as we know from our electrical field strength, that the distance that you move away from the centre of an object, and we treated all objects as point masses or point charges, but the further away you went, then it would be affected. And in fact, the same as with gravitation. So we will have a planetary object. Now, so if we just think of this as the Earth, now the gravitational field, as it would come out of here, it would look something like this. So here we would have a gravitational field extending out, and our arrows are always going to go in towards the centre of the object. We wouldn't generally say down. That could sort of be quite confusing. If you're standing on the surface of the Earth, whether you're in Australia or whether you're in here, you're always going to experience a downwards force. But it would be more correct to say that the force is acting towards the centre of the object. Like so. Field line spacing, as before, will determine or will give an indication of gravitational field strength, and so the further spaced the field lines are, the weaker the field. And what you'll find is that the further that you get away from the centre of the Earth, and so that's a key point, the further you get away from the centre of that object, is the weaker the gravitational field will become. And in fact, what our Newton's inverse square law of gravitation will give us would be F is equal to G m1 m2 over r squared. And so you can see it's inversely proportional to the square of radius. So the force is inversely proportional to the square of the radius, and it's directly proportional to m1, which would typically be the mass of the the planet or star, whatever is setting up the gravitational field, will have, just like electrical field strength, will have the object that creates the gravitational field, and then we'll have the object that's in that field. And more typically, what I'll usually do when I'm doing this is I'll write this equation as you can use M1, M2, but more typically I'll do big G, big M. Big M is the mass of the planet or the star. Small m, which is the mass of the object that's in the gravitational field, over r squared. Again, be careful with questions that start referring to altitude or height above a planet's surface, because we'll have the radius of the planet, and if it just gives you a height, if it says it's 36,000 kilometers above the Earth's surface, then you'll have to add in the radius of the Earth on top of that as well. Okay, so that is Newton's inverse square law of gravitation. G is obviously the constant in this. Big G is Newton's gravitational constant, and that is 6.67 times 10 to the minus 11, and that is Newton's meters squared per kilogram squared. So that's the constant. Incidentally, when Newton came up with this law, he didn't actually have any way to measure his gravitational constant, his big G, and he did it with proportionality. He was basically he said that force would be directly proportional to the mass of the planet or whatever, directly proportional to the mass of the object that's in there, and it's directly proportional to or inversely proportional to the square root of the radius, and that's really as far as he got with his law of gravitation. The actual constant, there's a number of different ways of doing this, and I think mentioned in the course notes are a couple of experiments. The first one there, which is talking about the Cavendish-Boys experiment, two physicists, Cavendish and Boys, did an experiment, and there's a couple of short clips that you can go to and watch from there. They're just very short, couple of minute videos. They're not technical in any way, it just shows you a couple of examples of what the Cavendish-Boys experiment was. And there's also one with Mascalin who did it, and he basically did an experiment next to Schiehallion. It's a mountain in Perthshire, which involved hanging a pendulum next to the mountain and trying to measure the deflection of this pendulum due to the mountain itself. The angles involved were incredibly small, but certainly the most common experiment to do to determine this big G, the Newton's gravitational constant, is the Cavendish-Boys experiment, and it goes something like this. You would have a bar. This bar would be set up with two large masses on it, and the bar would be suspended with a piece of wire onto the ceiling. So you'd have this piece of wire, you'd have a bar, and there'd be two heavy masses on it. It would be left to settle, and through analysis of the wire you would be able to get a spring constant almost of the wire, that is, if you were to twist the wire around and then let it go, the fact that you've twisted the wire, it will have a restorative force which will then make it spin around, and eventually it would go back to your original position. And so you could move this, you could let it go, and it would restore itself. And so you can do experiments to find out exactly what the restorative force would be, and therefore the point at which there's no force where it would be hanging. You could then place two large spheres, if I just do them here, and it does one on either side, and so this essentially just sort of doubles the force that you'll have for each of these. And what will happen is that this bar, the torsion wire, will then start to, well, there's a word for that, it would start to gravitate towards the larger sphere. It would spin very, very slightly. And again, the amount of movement is tiny, but what we can do to exacerbate this is that we can get a light beam. So we can shine a light beam, and if I get a ruler, then we can shine our light beam at that, and it's going to come back at an angle. So shine our light beam there, it'll come back at an angle. Now as this bends, the angle that it is going to move is going to change, and if we can then measure the amount that it moves, then we can get the amount that is turned, and from that point then we can determine our big G. It's worth noting you don't have to know how to calculate the big G value from this, but it's worth noting as an experiment to pay attention to. But as I say, look at the YouTube videos because there's a couple of examples on there. So just for completeness, we'll do a few worked examples on this, and the first one which we can do would be, I guess, calculate the force in the International Space Station by the Earth's gravitational field. And so for this, we'll obviously have Newton's inverse square law of gravitation, so F equals big G m for r squared. Now we need data, and so G, 6.67 times 10 to the minus 11. I don't know whether I can actually be bothered writing out the unit, but I will. There, now big M, mass of the Earth. This is at the end of your course notes. You'll have this appendix, which is going to have the data sheet and the relationship sheet for advanced higher and for higher, and whatever else that is, the stuff. I don't care. But it's also got this, which is data specific to RMA, and mostly it's data specific to astrophysics, the stuff that we're doing here, gravitation, and it gives you a lot of good stuff there. But as it is, we don't need to use that because we can get radius of the Earth, mass of the Earth, and the stuff that we need for here. So mass of the Earth, 6 to the 24. Mass of the ISS, let's ask Google. Google says it's 419,000 kilograms, 700. And we need the radius. Again, we're going to go and ask Google. Google says that it is an altitude of 408 kilometers. Now, we need to be careful here because this is the altitude. It's not the radius from the center of the Earth. So this is the height of the ISS above the surface of the Earth. So 3.6 times 10 to the power of 6 newtons. Now that might seem like a huge number, 3.6 meganewtons, and it's something that we don't usually encounter. But if you think the mass of the International Space Station is 4.2 times 10 to the power 5 kilograms, and the gravitational field strength of the wee g on the ISS is around about, I think it's about 0.8, 0.9 of what it is on Earth. And so on Earth, the force of, if the ISS was transported back to Earth, you'd be looking at being 4.2 times 10 to the 6, 4.2 meganewtons as the weight or the force that the Earth was applying to that. So that then makes sense after that. Okay, we'll do one more example. This is an example that's actually in the course notes, and so we'll have a look at that. From the course notes, we can see just what I'm calling the Earth-Moon system, but it could be for anything. It could be between the Earth and the Sun, or between any two massive objects. And what we're doing is we're looking for what we'll call a Lagrange point. And what that basically means is if you have an object here, and you place an object in that gravitational field, it's going to experience a force and it's going to accelerate towards that object. But if you place another object in that gravitational field, this is a bigger mass. Let's just do bigger mass and smaller mass. This is a bigger mass here, so placed here, it's gonna go to this one side. If incidentally they were both exactly the same size, and if you placed it directly in the middle, then the force of attraction from this mass and the force of attraction from this mass would cancel each other out, and you would have a net zero force. You would have balanced forces. But smaller mass, bigger mass, then you're going to have to take your object back towards, say, here, before you'll get the force of gravitation on this object from this object to equal the force of gravitation from that object on this. And this is known as the Lagrange point. So Lagrange point, the point at which the forces will be balanced between the two objects. And we can work that out from, and say if we would do the mass of the Earth and the mass of the Moon. So where is the Lagrange point between the mass of the Earth and the mass of the Moon? Well, we can do this, and this is I'm not going to say it's a common question, because it really isn't, but it's a question that is asked in textbooks certainly a lot. Whether you'd be asked to do it in an actual advanced higher paper, I question that indeed. You know the distance between the Earth and the Moon, so let's call that d, and then we could have this here as a distance x, so let's call this the distance x. And so the distance from the Earth to the Lagrange point, the distance between the Earth and the Moon, and whatever now. If we were to use our Newton's inverse square law of gravitation for this, because the forces are balanced, and so the force of E to x, Earth to point x, must equal the force of Moon to x. And so we're going to have G ME times mass of x all over now r squared, and in this case our r squared is just going to be x, so that would be x squared, and that's going to equal, again, big G, mass of Moon mass of whatever object that is, mass of the x. And then this is the tricky bit. We don't know this distance. We don't have it defined, and I mean, we could say, well, we could just call it y. But the problem that we're then going to find is that we'll have two unknowns. We'll have an unknown x and we'll have an unknown y. But we know mass of the Earth, mass of the Moon. We know the distance between the Moon and the Earth. And so it leaves us that the only unknown that we need, and we need to keep it that way, is x. But if this is d, then x, or this distance here, is going to be d minus x. So you just have whatever d is and take x away, and you're going to be left with that. And you can put that into there, d minus x squared. Okay, and that's going to be our basic formula, and from there we can work out. We need to, first things first, we can get rid of big G on both sides. We can get rid of wee m on both sides, and I'll just rewrite this. So me over x squared is equal to d minus x squared. I can cross multiply. Sorry, so we're going to go d x squared leaves us with this. We can then get rid of these squares here. Then now, so we have d is known, these two known, so we're trying to get now to just x on its own. And so the thing to do would be to, well, cross multiply again, bring, so d minus x is equal to x of this, so me, running in there, and I'm going to have to go up here, take this over to the side, and so we'll have d is equal to x. So it's a minus x, you move minus x over to the other side, it becomes positive x, so that's x plus, and we're going to have x over this bracket me. There. Take x's out of the brackets, or put x's to a bracket, and then 1 plus the square root of e. And now finally take this across. X equals d and there you go. And if we put in the data of that, then we can get what find a value for the Lagrange point. So if we make the substitution and we type in the number in the calculator, then we'll get something. This. So what is it? 3.46 times 10 to the power of 8 meters. And so at a distance of 3.46 times 10 to the power of 8 meters from the centre of the Earth, we would have a point at where there would be no net gravitational force on this. Now, you can see as instead at the very start of this, there's an example in here, and the keen-eyed among you might notice that my rearrangement here is completely different to what my rearrangement was here. But at the end of the day, 3.46 times 10 to the power of 8, 3.46 times 10 to the power of 8. Finally, we're going to talk about gravitational field, or gravitational field strength around an object. Now, going back to our initial point in the national definition of gravity, where we would have had W is equal to mg, and g would have been defined as gravitational field strength. And so this is the force per unit mass that would be applied to an object. And if we're going to analyze this, so we would have the force here, the mass, and so this would be mass of object in the gravitational field. Grav field. Then we can get a sort of analysis of what Vg is. Well, first of all, Vg would be defined as the force per unit mass. Okay, and so G is equal to force over m. But if we're to put this into the inverse square law of gravitation that we have, F is equal to big G m over r squared, then the mass that we're actually talking about is this one here. And so if we are to look at that, then we'll see that Vg is equal to big G m over r squared. And here we get a term for the gravitational field strength at a point that's a distance of r away from an object. And if we were to draw a diagram of this, then, and this is exactly the same as electric field strength, and how electric field strength would compare to Coulomb's law. And so with Coulomb's law, we're looking at two charged objects. With Newton's inverse square law of gravitation, we're looking at, again, two massive objects. But when we're looking at just the simple field, the electric field or the gravitational field, we only have that one object, an object in isolation. And so what this will tell us is the gravitational field strength at any point is determined purely by the mass of the object and the distance from the center of the object, like that. So here we would have our r, and then we would have the mass of the object as well, which is there. So that's going to give us our gravitational field strength. And as I drew in the previous page, we had the gravitational field, which we're going to draw like this. The arrows are going to be pointing in towards the center of the object. Secondly, we could also do gravitational field around two objects. Now, if we're going to assume that the objects are both exactly the same, and then come up with an electric field lines. Remember, this is one of the learning intentions. I'm just going to start like this. I should have probably done them a little bit closer together, but we're going to have this curve out. Like like so. And again, going back to previously what we were talking about, is that your Lagrange point would be that point right in the very middle there. And obviously this is a representation of the field lines, so you could add in as many field lines as you wanted to get that, again with the caveat that none of the field lines are going to touch. You would put arrows in, the arrows would always go in towards the centre of the object, like so. But what if they weren't of equal mass? Well, you would just shift, as in the Earth-Moon system, you would shift the Lagrange point closer to the smaller object, and then the lines would change correspondingly. So we would have mass, just very quickly. And so we would have something that looked a bit like this. And so that would be shifted along towards the smaller object, the smaller mass object. So that's what we'll do for this lesson just now. I will be back shortly with more, but for now, you have the questions in the course notes to do. You have then some. I'll set you an assignment on Classroom with some more work on gravitation to do. But okay, well, thanks for watching, and I hope you're well. Bye bye.